Okay, welcome everyone to November's IGAC ECR seminar. Today, Sachin is going to be leading you through it. And for those of you this is the first time you're here, we have a monthly seminar or workshop. Next month, we also plan to have a seminar in just about 2 weeks. So if any of you is interested in giving a talk, then we still have one spot open for the 5th of December. Let me know. And otherwise, I will hand it over to Sachin to lead us through today.
So today I'll be introducing with two speakers, two highly energetic speakers for today's seminar. So first we have Dr. Maria Angelaki. She has done her bachelor's degree in chemistry from University of Crete, followed by master thesis in the division of physical chemistry. In 2021, she defended her PhD in physical and analytical chemistry under the supervision of Dr. Papadimitriou and Professor Kannakidu, where she investigated the reactions of several furans with major tropospheric oxidants, focusing on their kinetics and mechanistic pathways. In 2022, she joined the group of Dr. Christian George at IRCLN as a postdoc researcher, where she focused on heterogeneous chemistry and interfaces facial processes. And her work was specifically focused on spontaneous formation of OH radicals at the air-water interface of inorganic and organic particles, examining the underlying mechanisms and the factors that influence oxidant formation. Since October, she has been working as a postdoc researcher at Aarhus University in the group of Dr. Mott, where she is studying the cloud forming ability of secondary organic aerosols produced from the reactions of VOCs with nitrate radicals. And apart from that, she is also a co-chair of the Fundamentals of Atmospheric, Chemical and Physical Processes session for the 2026 IGAC International Conference. As we know that it's going to happen in next year in September 7 to 11 in Crete. So yes, today she will be talking about particle air-water interface, the unknown source of atmospheric oxidants. So let's welcome her to start her presentation. So before that, I would request everyone, if you have any questions, you can post them in the chat box, or you can unmute yourself and ask at the end of the talk. So thank you. Maria, you can start.
You're muted, Maria.
Okay, this is automated. I don't really do it. Thank you, Sachin, for the introduction and all of you for this opportunity. I'm happy to share some results from the work that I did as a postdoc in IRCLN. I can probably skip that. Yes, perfect. With all of these people under the supervision of Christian George and in close collaboration with James Donaldson from the University of Toronto. So the topic of today's presentation is the unknown source of atmospheric oxidants, which is basically the particle air-water interface. So the Earth is covered 70% by water, and it's full of various interfaces. And interfaces are important because they promote chemistry. So studies have shown that reactions are thermodynamically favored at the interfacial region compared to the bulk. And for this reason, chemical reactions can be accelerated up to 100 times at the interface compared to the bulk. Many groups have reported the spontaneous reaction of a reduction of metal ions at the interfacial region. And where I will focus today is a finding that we had the past few years, which is the spontaneous formation of OH radicals at the air-water interface. And this is happening without the presence of any catalyst, light, or chemical precursor. Everything is starting from this reaction where the OH anion of the interface exists as an ion pair and can undergo charge separation, producing OH radicals and an electron. And this is happening either due to the presence of a strong electric field in the interfaces and because the solvation properties of the ions are different in the interfacial region compared to the bulk, making this to happen easily. So to directly see OH radicals is difficult. What we need is an organic compound that will react with OH radicals, and either we can follow the decay of the organic or the production or the formation of products. A really good proxy for that is terephthalic acid, that it reacts fast with OH radicals and can produce hydroxyterephthalic acid, that I will call it as TOH. TOH can be observed in nanomolar level with fluorescence spectroscopy. So in our group in 2022, we started to do some experiments where we just created terephthalic acid solutions, and we took 2 beakers. One beaker we fill up to the top with the solution, and in the other beaker it was half full, meaning that we have a water interface. We were sampling a small amount of this solution daily for 1 month or more than 1 month, and we analyzed the liquid in order to see if TOH is produced. And we saw that only in the beaker that has a water interface, TOH could be formed, meaning that we have OH radical production. And the TOH was formed in nanomolar level. Our next step was to nebulize the solutions and to see if TOH will be formed in nanometric droplets. And we did see the TOH production in millimolar level, meaning that OH is enhanced when we have droplets, environments of higher surface to volume ratio. And also we saw that OH radicals can be desorbed in the gas phase using organic gas phase scavengers like cyclohexane. So this process also leads to the H2O2 formation. 2 H radicals can be recombined to produce hydrogen peroxide, or the electron can react with oxygen, produce O2-, that then will react with H cations, producing HO2 radicals, and that via subsequent reaction will finally lead to the formation of H2O2. So in 2022, the ZER group in the study of McGrady et al., they saw that H2O2 is formed in micromolar level in nanometric droplets. And this is not the first study, but for years, people were arguing if all of this process is happening due to the nebulization artifacts. So the answer had come in 2020 from, again, the same group, where they created droplets by not via nebulization, but by condensing water vapors in cold substrates. And in these droplets, they saw the formation of H2O2, meaning that the nebulization argument of artifacts was eliminated with the study. So the chemistry is happening. And since it's happening in our group, we wanted to investigate the H2O2 formation at submicron aqueous particles. But to have stable nanometric droplets is difficult, because due to the Kelvin effect, the droplets will be evaporated, and in the end, you will not measure anything. So we need a salt to lower the vapor pressure and stabilize our particles. So we ended up mimicking marine environments, and we produced droplets that containing Na2SO4, NaCl, NaBr, and NaI. And we investigated the formation of H2O2 as a function of the type of the salt, the concentration, and the pH. Our experimental setup is this one. So using several carrier gases, we nebulize salt-containing solutions using glass nebulizers in order to avoid the presence of metals in our system. We generate the particles. The particles travel inside a glass flow tube reactor for roughly 10 seconds, and at the end of the reactor, they impact on a glass volume, and we collect the liquid droplets and we analyze them. And to measure the H2O2, we used a direct method, which is an H2O2 analyzer. So we're passing to the results, and we can see here the H2O2 that is formed in Na2SO4 and NaCl systems. And we can see that in the bulk, we don't have H2O2 formation, but when we spray it and we create the particles, we have around 60 nanomolar of H2O2 in air environment. So how this is happening? Again, this reaction either from the recombination of OH radicals or via the pathway of the electron. To investigate more the contribution of this pathway to the total process, we did experiments in nitrogen. So with dotted line here, you see the level of H2O2 that is produced in when we have N2, only N2 in our system. And we can see that the H2O2 was significantly decreased. And O2 plays a key role in all of this process because the first reaction here is in equilibrium. If you don't have oxygen to scavenge the electrons will react back with OH radicals, forming the initial OH anions. But when you have it, the whole equilibrium is shifted on the right, promoting the products formation and not the reactants formation. So oxygen is really critical for this chemistry to happen. And since we have oxygen in the atmosphere, is a big pathway for H2O2 production. Then we changed the salt and we went to NABR. So we saw with NABR in air environment that the H2O2 formation was significantly increased. And what is happening is like the OH minus, Br minus can exist as an ion pair, meaning that it can go charge separation and produce Br radicals and electrons. By increasing the amount of electrons in our system, we enhance the contribution of this pathway that leads to the H2O2 formation. And our PhD student, Carrera Mendes da Silva, did a much more thorough work in the investigation of the type of the anions, and he studied several ions. And in this study, we saw that the type of the anion changes the solvation properties of H minus at the interfaces, and this is the key driver for the H2O2 formation and the amount that finally will be produced. So next step in my study was to see the effect of ion concentration on H2O2 production. And in this plot, we see the concentration of H2O2 as a function of the salt concentration. Focusing on the blue and the green symbols, we see that when we have Na2SO4 and NaCl droplets, the H2O2 is totally independent from the salt concentration. But when we have an NABR, we have a different behavior with H2O2 to increase in the beginning and then finally at a certain concentration reaches a plateau and it's not increasing anymore. So this kind of behavior is a typical Langmuir behavior that suggests the surface process. And what is happening is that as we increase the concentration of the salt, we increase the concentration of electrons promoting again this pathway. But why Na2SO4 and NaCl don't do that? To investigate that, we sprayed solutions with mixture of NABR and NaCl. And here is the black point that they indicate that the amount of H2O2 that is produced is defined by the NABR and not the NaCl. So NaCl and also Na2SO4 are not involved in the chemistry. They just there to sustain our particles, and basically they represent the water. Our final step was to see the effect of the pH in the droplets. So we prepared different salt solutions from a pH of 4 and 10, and we nebulized them. We created the droplets, we collected them, and we measure the pH of the droplets. And we can see here that in N2O2 environment, the pH of the droplets is more or less the same as the bulk, which is what we were expecting. So in these experiments, we changed the concentration of H minus about 5 orders of magnitude. So one would expect that the amount of H radicals and electrons would significantly increase when we go to alkaline conditions, and that's the amount, and thus the amount of H2O2. But we didn't see that. In this plot that describes the H2O2 formation as a function of the pH of the droplets, we see that by moving to alkaline conditions, we just had a small increase in the H2O2 formation. And this is something that until today we cannot understand. And people in Lyon right now they investigate more. One possible explanation could be that the kinetics of all of the mechanistic scheme are strongly pH dependent, and we don't have rate constants for that. But again, we don't have a solid explanation why this is happening. But still working on that. So these experiments performed in N2O2 environment, but in the atmosphere we have CO2. So we repeat the experiments with compressed air, and focusing on the alkaline conditions, we saw that the pH of the droplets was decreased compared to the one of the bulk. And this is due to the acidification in the presence of CO2. No big surprises here, but what it was surprising was that in alkaline conditions, the amount of H2O2 was decreased significantly by changing the bath gas. So having a compressed air, our first thought was like we have an impurity, maybe an organic, a VOC in the compressed air that eats the OH radicals. So we repeat these experiments with pure N2O2 plus 400 ppm of CO2 pure from a cylinder. And these results are with the black points here, and we can see that are in excellent agreement with those obtained in the compressed air. So this is not an impurity, this is a chemistry that's happening. And what is happening is that the carbonaceous species that exist in alkaline conditions react really fast with OH radicals. They scavenge the OH radicals, decreasing the H2O2 formation via OH recombination. So this is what we learned from these experiments. So in total, what we saw is that inorganic and sea salt particles could be a new road for oxidant production in the atmosphere that needs further investigation. But in the atmosphere, we don't have only inorganic particles, we have also organic particles. And this is where I will focus in the second part of my talk. And what we wanted to see is that if we have an organic particle that is in the presence of humidity, if water vapors will condense on the particle, create their water interface, and thus OH radicals. And what we wanted to know, if this is happening, is the amount of H radicals that is produced sufficient to oxidize the organic particles? And if yes, is that important for the atmosphere? So we studied 3 different systems. Our main system was citric acid, because citric acid is a great proxy to study organic particle processes. We studied also maleic and aconitic acid. I will focus on the results of the citric acid for the sake of the time. So here is our experimental setup, and we used a carrier gas, compressed air, to nebulize citric acid solution. We create wet citric acid particles that we dry them until the humidity is around 0 to 2%, and finally polydisperse dry citric acid particles of a maximum of the size distribution 100 nanometer enter into a flow tube reactor. From the other side of the reactor, we pass air that we humidified it. So what is happening inside the reactor is that water vapors and organic particles interact with each other, and at the end of the reactor, we have filters, we collect the particles, and we analyze offline the chemical composition using liquid chromatography coupled with mass spectrometry. In order to avoid some artifacts that can happen onto filters, we did also online measurements with an instrument that is called Wally-Focusame. We had NCPS to monitor the growth of the particles and the size distribution, and also RH probes to see the humidity of our experimental conditions. So first of all, from the reaction of citric acid with OH radicals, we know that we expect to see malonic, malic, and glyoxylic acid. And in this plot, we can see the product's concentration as a function of the humidity. So one really important result from this plot is that at zero humidity, dry conditions, we have no products formation. And only if we have a small amount of water vapors in our system, we see products formation. So this means that the chemistry is water driven, and it's not related with artifacts from the nebulization. I will do a small pause here just to say that since we saw that these products are formed, we wanted to know also if all of this is thermodynamically favored. So we did a theoretical study to support our experiments, and we saw that citric acid, but also other small carboxylic acids can undergo spontaneous decarboxylation as soon as we have hydrogen abstraction. So all of these products, the pathway that leads in these products, the barriers are really low. The final products are below the initial reagents, meaning that we have exothermic reaction. So all of this is favored to happen. So our experimental results are supported also by theory. So coming back here, what we can also see is that the product's concentration is increased as a function of the humidity. And again, this is happening only in the presence of oxygen, because all of these concentrations are going close to zero when we have nitrogen environment. And the most interesting feature of this plot is that the product's formation is occurring before the deliquescence of the citric acid particles. And this is a first indication that is a surface process. And we wanted to dig a little bit more in that. So we did size resolved measurements, meaning that we put inside the flow tube reactor not polydispersed particles, but just one size of particles. And the size was ranging between 65 nanometer to 250 nanometer. And we measure the product yield of the malonic and the malic acid. And we saw that as we increase the surface to volume ratio, we have higher amount of product formation. And that verified that all of this is happening in the surface of the particles and not in the bulk. So final step was to evaluate the atmospheric significance of this process. And until now, we know that if an organic particle is in the atmosphere, what will happen will be the gaseous OH radicals to be uptake onto the particle and start its oxidation. So we wanted to see how important is the spontaneous OH production at the air-water interface versus this process. So Razul et al. Did a really nice study where in their model, they tried to predict how would be the organic decay in a particle within 24 times when it is exposed at two different concentrations of OH radicals. So we can see with green line that if an organic particle is in the atmosphere at low concentrations of gaseous OH radicals, it will have a decay of 3% during 24 hours. And when we have higher concentration of OH radicals, let's call it daytime scenario, it will have 25% of decay. So what we did was to take our data, the lowest and the highest value that we observed, and we calculated how much would be the decay of the organic due to the interfacial OH formation. And we can see that it can vary between 6 to 30%. And what is important here is that maybe during the day, the spontaneous OH formation would be a negligible oxidation pathway, but during the night, it's potentially an important pathway that should be considered and, of course, investigated more on other complex systems to see if this can change the oxidation capacity of the troposphere. So to conclude, we saw that inorganic particles can produce OH radicals and H2O2, and also air-water interfaces of organic particles can lead to their aging, oxidation, changes in their composition, and maybe it's an important unknown oxidation pathway. Right now, people in Lyon, they still investigated this phenomenon. They try to see the temperature effect, the surfactant effect. They try to see how nitrate and sulfate chemistry will affect all of this process. And with close collaboration with theoreticians, we try to do calculations in order to assess better and understand better why this is happening. So I will take a moment to acknowledge the care team that I was working there for 3 years. Christian Georges, my supervisor, Jamie Donaldson, the close collaborator that without them, nothing would have happened. the two PhD students, Ion and Laurentio, that helped me in all of this process, and all of the postdocs and the teams of the care and the other members of the care team. I would like to acknowledge Arcelion, the foundings, and all of you for your attention. So I'm happy to take questions.
Maria, for a very interesting talk on air particle interactions. I have like simple questions in the slide number 11 where you are generating the particle of a particular size. So how you were able to generate the particle? Like you were using any kind of SMPS to monitor the particle size, or how means what are the instrument to in the slide number 11?
That is slide 11. Okay.
Yeah.
So,
In the where you were drying the citric acid solution.
Yes. So your question was how I generate the monodisperse?
Yeah, however, were to polydisperse the dry Ca of 100 at a particular size without having anything like any kind of instrument or.
Okay. So I was not clear enough. In these experiments, is polydisperse with a maximum of 100. Of course, we have from 60 nanometer to 250 nanometer the full size distribution. And when we did the monodisperse measurements, the size resolved measurements, we saw that here, before the entrance of the reactor, we put an aerodynamic aerosol classifier to select only one size of particles. And we did that with this instrument, which has some advantages compared to the DMA because it does not involve any charges, and also the particle losses are less. But also we did experiments with DMA to verify our results.
Okay. I have one more question, then I will take questions from the chat box. There, again, the injection, the H2O2 concentration decreased with the increase in the injection rate. I think it was in the first few slides, first 5 slides, I guess.
Yeah, the study of the literature. Yes, I'm going there.
So, like, I was wondering, like, what would be the reason for the decrease in the H2O2 concentration over there?
So by increasing the nebulization rate is something that we also see in our group, because this is not study from our group, you decrease the residence time in your flow tube. So less time to react, less amount of H2O2.
Yeah, perfect. So there is
either I will stop sharing my screen because I cannot see any question, or basically you. So is that okay for you?
Yeah, I will read out for you. So
Yeah.
there's a question from Arpit Avasthi. Here's question like experimentally, how did you observe if there is any OH radical increase or decrease with solar radiation?
With the what?
Solar radiation.
Solar radiation. Okay. So all something that I should have mentioned, all of our setups are covered with cloth. All of our chemistry is happening in the dark because we didn't want to involve any light, because the primary reaction is not the one of H2O2, it's the one of H radicals. So we don't want to support the spontaneous claim of that everything was covered in the black.
Okay, great.
Are there any other questions?
Yeah, I think, yeah, thank you, Maria, for this wonderful talk. There is, I think, no more questions in the chat box, but you can feel free to contact her if you have any questions regarding H2O2 production and like radical interfacial chemistry. So
Sure, thank you so
we'll
much.
move. Thank you. So moving forward to the second speaker for the seminar, we have Bradley Isenor. He is a fourth year PhD student at the University of Toronto, Canada. He received his Bachelor's of Science honors in chemistry with a minor in biochemistry from Mount Allison University in 2022. As a part of his honors thesis, he studied the oxidative potential of fine particulate matter emitted from traditional and improved biomass cook stoves under the supervision of Professor Jenny P.S. Wang. Then, after graduating, he started his PhD in Professor Arthur Chan's research group at the University of Toronto in Environmental Chemistry Department. And his PhD research investigates the oxidation potential of particulate matter and how it is impacted by wildfires using both real world wildlife events and simulated burn experiments. So today he will be giving us a presentation titled Assessing the Oxidative Potential of Aerosols from Canadian Wildfires and Their Fuels. So let us welcome Brad. You can say it, okay.
Great. Thank you so much for the introduction. Can you see my screen?
Yeah, we can see.
Okay, perfect. Let me just... Okay, yeah, thank you for the invitation to give this talk. My name is Brad. Like Sachin said, I'm from the University of Toronto in Professor Arthur Chan's group. And today I'll be giving my presentation on assessing the oxidative potential of particulate matter from Canadian wildfires and their fuels. So just beginning with some motivation, as you're all likely aware, wildfires are a major issue globally, and they can be extremely dangerous and destructive. Unfortunately, as a consequence of climate change in certain areas of the globe, like here in Canada, wildfires are expected to increase in their burned area, and also the frequency of large fires are expected to increase as well. This has been particularly evident in recent years, here in Canada especially, where in 2023, Canada had the greatest area burned in recorded history. And then this year, 2025, was actually the second greatest year of area burned by fires already. The problem with increasing wildfire presence isn't only that they're destructive, but that they emit massive amounts of smoke into our atmosphere, which can have impacts on our climate and also on human health. And one of the pollutants found in the smoke that we're all familiar with is fine particulate matter, which are those small particles that are able to penetrate deep into our respiratory tract. And these fine particles are well known to be associated with a variety of negative health outcomes. However, some recent epidemiology studies have suggested that fine particulate matter from wildfires could actually be more harmful than regular ambient particulate matter on a per mass basis. And this is likely due to differences in their chemical composition. Unfortunately, there's still many unknowns regarding wildfire chemistry and what chemicals are actually driving these changes in toxicity associated with it, making it an important area of research. One of the prevailing hypotheses for why aerosol are harmful and exhibit differences in their harm is due to their ability to deplete the body's antioxidant defenses and then generate harmful reactive oxygen species, such as the hydroxyl radical. And this can induce what's known as oxidative stress. And we call this the oxidative potential of particulate matter. And it's considered a better predictor of the adverse health effects of fine particulate matter than just PM concentration alone. And this is because that oxidative potential starts to consider differences in aerosol chemistry that are missed when just discussing mass concentration. And so luckily we can measure oxidative potential in several different ways. One of the most common methods is through measuring antioxidant depletion. And that's seen on the left-hand side of this reaction I have on the screen. And so we can measure this through different ways like acellular assays, such as the DTT or dithiethridol assay, which I'll discuss a little bit later. And additionally, we can measure species that have the capacity to generate reactive oxygen species, like environmentally persistent free radicals, or we can directly measure the generation of reactive oxygen species through electron paramagnetic resonance. So in this presentation, I'm going to discuss two of my projects. The first, which is already published, and looks directly at wildfire smoke samples that we collected from the 2023 Canadian wildfires. And another project I'm still working on where we burn different fuels in a fire lab to gain insights into their emissions. So we can get right into it with my first project here. Like I said earlier, 2023 was Canada's worst year for wildfires. We had massive amounts of smoke that were emitted into the atmosphere, and that was felt across North America. You can see here on this map here I have is that all these kind of red dots are places that were identified as having fires in Canada. Luckily, we were ready for sampling of these wildfires, and we had 3 sites to assess how the influence of these fires impacted the oxidative potential of aerosol in different environments. And this was to carry out our experiments. In different environments. And so, yeah, to carry out our experiments, we collected wildfire and non-wildfire particulate matter from an urban site at the University of Toronto, another urban site at the University of Illinois Urbana-Champaign campus, and then a remote or rural site that was in East Trout Lake, Saskatchewan. So to assess the oxidative potential of our samples, we used the dithiotridol or DTT assay. And this is an acellular assay that measures the rate that DTT, which is a model antioxidant, is oxidized over time when it's incubated with particulate matter. When we normalize this by the rate at which it's oxidized by mass, we get the oxidative potential. And then when we normalize it by the volume of air sampled, we can get oxidative burden, which is more of an exposure metric to redox active chemicals. And so we chose the DTT assay as it's one of the most commonly used metrics for assessing the oxidative potential of particulate matter. And it's sensitive to metals and oxidized organics, both of which we believe to play a role in the oxidative potential. Moving into our results now, when we looked at how wildfire influenced the oxidative potential at the 2 urban sites, Toronto and Champaign, we found that the wildfire influence did not increase the oxidative potential at either of the sites. In fact, there was no significant difference that we were able to statistically measure between the wildfire and non-wildfire periods. Since wildfire particulate matter is considered to be more harmful than regular ambient particulate matter, this was a little surprising at first. However, it does actually align with a previous study done by True et al., who used the ascorbic acid assay, a different oxidative potential assay, and found the same result, that there was when there was wildfire influence in a previous year in Montreal, they didn't see any difference between the oxidative potential on wildfire versus non-wildfire influence days. Looking at our rural site now, what we did find here was that there was actually a slight increase in the oxidative potential at this rural site. We couldn't determine if this was actually significantly different or not, given just how few samples that we had for wildfire and non-wildfire samples. Yeah, but one interesting thing we did notice was that the wildfire samples at this rural site did seem to be slightly higher than the Toronto and Champaign site. And this had us kind of questioning why this might be the case. And it's something I'll discuss a little bit later. Taking a quick look, though, at oxidative burden first, which is, again, essentially the exposure to these DTT oxidizing species, it's clear that during wildfire periods, oxidative burden is dramatically increased, especially when we look at the y-axis here, where this is a log scale, right? And so given that that oxidative burden is a product of oxidative potential and PM mass concentration, it's clear that this increase is actually primarily being driven by increased PM exposure, as evidenced by that less dramatic change in oxidative potential that we just saw. Due to our samples being limited, we weren't able to do much in terms of chemical characterization of our samples. But luckily at U of T, we did have an EXACT, which was sampling continuously, and that measures metal concentrations in the air. This is important because metals like copper, iron, and manganese are redox active and are important in their contribution to oxidative potential, especially in urban environments. Unsurprisingly, we observed no significant difference in concentrations of redox active metals in the air during the wildfire influence periods, but we did see a significant difference in potassium, which is a biomass burning tracer. However, due to increased contributions of non-metallic species from wildfire particulate matter, the fraction of redox active metals in PM2.5 decreased significantly, actually by over an order of magnitude for each of those redox active metals. Despite this decrease, though, as shown before, there was no significant decrease in oxidative potential of Toronto wildfire PM. And so this suggested non-metallic species are playing an important role in the oxidative potential of wildfire PM samples that could be offsetting that loss by the contribution of metals. So going back to my question from earlier of why wildfire PM might have had higher oxidative potential at the rural site compared to the urban sites, we decided to look at the transportation of smoke from the wildfires using T-fin back trajectories, which is essentially using a high split back trajectory and looking at how far back in that back trajectory there was an interception with a fire hotspot. And so we looked at how many interceptions occurred within 24, 72, and 168 hours. And this was done to estimate the age of the wildfire particulate matter. We found that the rural fires at East Trout Lake had actually undergone much shorter transportation than urban sites, meaning that they were likely fresher wildfire emissions. And that might be actually suggesting that less aged particulate matter has a greater oxidative potential. One reason for this could be that during shorter oxidative aging, organics may have undergone some sort of functionalization, which increased their oxidative potential, followed by a fragmentation, which may have led to the decrease in oxidative potential. And this was exciting because it actually aligned with some observations of aging of lab burn samples, but this really hadn't been shown with real-world wildfire emissions before. However, it should be noted that with these results, that these fires are in different locations. And so the location of the fire and other burning, other factors related to burning may have also contributed to differences in the oxidative potential that needs to be considered. So just key takeaways from this project: wildfire influence didn't increase oxidative potential in the urban environments. It did seem to maybe slightly increase it in the rural site. But that might have been related to lesser extent of aging. We found that non-metallic species seem to be contributing an important part of the oxidative potential in wildfire particulate matter. And that extreme PM concentrations really are what drives our exposure to these harmful oxidizing species. And so in the future, we'd like to look more into this aging, especially at really long timescales. Moving on to my more recent work now. So this is stuff that I'm still working on, a lot of data analysis and still some tests that we want to do. But this was done as part of the BBCAN 2024 Fire Lab campaign. So a bit of motivation and background is that BBCAN is a Canadian research network, and it was started to improve the understanding of Canadian wildfires. And this Fire Lab campaign aimed to understand fuels consumed in boreal forest fires, as those still remain poorly understood in terms of their emissions. So in preparing for this campaign, we also realized there was another emerging field of interest, which was fires at the wildland-urban interface, or the WUI, which is a growing area where wildland vegetation meets human development. And fires at the WUI are unique as they contain a variety of anthropogenic materials not found in nature that, when burned, have different chemical compositions to regular wildfire smoke and can contain toxic chemicals not observed from natural fuels. Since fires are expected to happen more often at the wildland-urban interface as it expands, and their emissions are poorly understood, an assessment of the oxidative potential of both natural and built fuels is necessary to understand modern wildfires. And so, as I mentioned before, this is part of this Fire Lab campaign in Edmonton, Alberta. And during this campaign, we burned 11 different fuel types, 4 of which were different types of plastic materials. We used a treated wood that we burned as well, that was also burned with the plastics to initiate and sustain plastic burning and simulate real-world burning in homes. 6 different natural fuels, 3 of which we burned at 2 different moisture levels. And in this presentation, I'll keep things simple by separating things into 2 fuel categories, natural fuels and built fuels. Here, I have a picture of online measurements that we did with, this is the burn lab setup. So I'll point your attention to the gas line here, where we had a whole bunch of different online measurements that were being taken over the course of each burn. But we also had a particle line, a whole bunch of measurements being taken there, which is really great to have so much data available to us. But one of the key things was that we took a filter that was PM 2.5, and that was used for the oxidative potential in terms of the DTT assay, reactive oxygen species, and EPFR. I'll be talking about that one today. So the way our burning worked was we would heat the fuels using that heating lamp pictured here. And to get the fuels to begin flaming, we would use that heating lamp, get them up to temperature. It would go from flaming to smoldering, and then smoldering to extinguished. In the case of plastics, this would be slightly different in terms of we would get our wood blocks flaming first, and then add the plastics. That way the plastics didn't start to melt and lose their composition before any sort of flame would happen. And we're trying to mimic that sort of flaming burning that would happen in a house where the house would catch fire and start to burn the plastics and stuff on the inside there. And so, as I mentioned before, in addition to the DTT assay, we measured environmentally persistent free radicals. And this was done by inserting just a filter into an EPR tube and into the EPR. And then we'd get a nice spectra like this. We could quantify the amount of EPFR from this using a calibration curve with a known standard tempol. But we could also determine other stuff like the G factor to determine whether it's carbon or oxygen-centered radicals, as well as we could get the peak-to-peak line width. Reactive oxygen species are a little more difficult to measure. These are really short-lived when we're trying to measure things like the hydroxyl and superoxide radical. So what we end up using here is what's known as a spin trap. And so our radical forms an adduct with the spin trap, BMPO in this case, and it forms a more stable, long-lived radical. And we can measure these because they have a half-life of about 20 minutes, which is enough to measure them in the, gives us enough time to measure them in the EPR. And then we can use spin-fitting simulations to actually figure out what radicals we're measuring and the relative abundance of those as well. So moving right into our results now, we found that when we group natural fuels together, their mass normalized DTT activity, or that oxidative potential, was significantly greater than the built fuels by about 54%. However, when we looked at the EPFR, and we normalized that by mass, we found that the built fuels were actually higher than the natural fuels, and that was about 89% greater. And so when we looked more into the EPFR to get a little bit more information about these, we found that among natural and built fuels, the G factor was pretty constant at about 2.0017. So that's characteristic of carbon-centered radicals. And we also found that the peak to peak line width was actually quite narrow for both the natural and built fuels, suggesting that they're probably both largely just all carbon-centered radicals, not much oxygen-centered radicals. Taking a look now at the oxidative burden, or again, that volume normalized DTT activity. Each point here is a different burn or sample. We see it's strongly correlated with PM 2.5 concentration. It's not really surprising since oxidative burden is essentially just that product of oxidative potential and PM 2.5 concentration. And so we wanted to separate that into the built-in natural fuels. We didn't see much of a difference here. Even when we zoom in, you can see the slopes are quite similar. The intercept is a little bit off for the built fuels. So slope and intercept a little bit lower for those built fuels. And that's probably just coming from the oxidative potential really being lower there. When we look at how moles of EPFR compare to PM mass, again, here we actually don't see much of a trend right away. But when we separate it into the two fuel types, there we go. We do see quite a distinct trend between built and natural fuels in this case, where we see the built fuels are increasing in terms of as more mass is being collected on our filters, we're seeing more EPFR as we would expect. But natural fuels, we don't see that. And a little strange. It's almost as if we've reached the maximum amount of EPFR. They're being saturated or something on our filter with these built fuels. And that doesn't really make too much sense to us. And so we wanted to investigate that a bit more. Okay. Yeah, there we go. One idea we had to why these differences might have been is the actual types of flaming that were dominant, the types of burning that were dominant for built versus natural fuels. Built fuels were primarily burned using this flaming combustion. However, the natural fuels underwent different types of combustion. So grass was primarily like all flaming versus something like peat when we were burning it. That ended up smoldering quite a bit and contributing a lot to the mass. And when we found this paper by Fung et al., they found that with pyrolysis, produced very little EPFR, while flaming contributed a lot to the EPFR content. And so we wanted to look at if we could estimate the flaming mass fraction from of our PM 2.5 to see if that maybe explained this difference. And in fact, we found that it did. So you can see that these really high mass samples that had low EPFR underwent primarily smoldering. They had really low flaming mass. And so next, what we wanted to do was plot on the x-axis instead of PM 2.5 mass, flaming PM 2.5 mass. And here you see that it tightens up and that it that seems to follow a more logical trend of increasing PM 2.5 mass means increasing EPFR, right? It's not as clean as maybe the built fuels were on their own before, but we don't necessarily expect that. We still expect, even if flaming is contributing most, if not all, of the EPFR, that the different fuels would still have their own differences as well. But still a pretty good correlation and seems to explain that difference there. Wrapping things up here, just last result, we still are working on the analysis of our reactive oxygen species, but we did see some clear, distinct trends just in our preliminary analysis. One being that we were able to see a confident signal from 75% of our natural fuels. And they had varying amounts of hydroxyl, superoxide, and carbon-centered radicals. But with our built fuels, we really didn't see any reactive oxygen species, which was quite surprising. You'll see that all we saw here was essentially an EPFR signal, which is kind of which isn't really one of those ROS. We have some ideas for why this is the case that we're in the midst of testing. And so hopefully in the near future or whenever this paper is published, I'll be able to share our results and explanation for that. Wrapping things up here, I'll say just key takeaways. EPFR are higher for built fuels, while DTT was greater for natural fuels. The mass of the PM from flaming combustion seemed to really determine how much EPFR we observed. And then that the reactive oxygen species were observed in primarily all of our, in a lot of our natural fuels, but essentially nothing in our built fuels. And there's a whole bunch of future work we have to do with other data that were collected from the campaign and sort of just our interests that we're following right now. Finally, I want to say a big thank you to those who contributed to this work. A lot of people were helped to do this research. Also, the funding agencies that made the work possible, and to my lab group who have been really helpful and supportive. So thank you for listening, and I'm happy to take any questions.
Thank you, Brad, for an interesting talk. Coming to the questions, like I have a few questions regarding the number of samples that you collected for the filters. So it was like it was a kind of very few samples, and summarizing or concluding things with those few samples are like, is it significant kind of stuff, like with n equal to 7 or n equal to 10? So what do you think, if you are going to increase the number of samples, is the result going to change?
Yeah, that's hard to say. I think ideally, obviously, we'd love to have more samples. The problem with wildfire sampling is that you're kind of just at the whim of whether there's going to be a wildfire that happens, whether it's going to intercept or not. And with this oxidative potential work, collecting enough of each sample to actually be able to run the assays and such. Would we expect to see a difference? I think with the Toronto and Champagne one, given just how similar they are, I'd be surprised if there really was much of a significant difference there in terms of the wildfire. I think the biggest thing that would impact a difference would be the proximity of another fire. The fires for Champaign and Toronto were primarily all coming from the Quebec wildfires. And so they had all both been aged quite a bit. And they'd been transported for a long period of time. But if, say, there was a fire that happened locally close to Toronto, then I could see that that might have made a bigger impact as well. But that might also complicate things in considering it the same type of wildfire.
Okay, nice. And I think we have one more question from chat, from Asmi Mishra. She's asking, like, in the first study, what non-metallic species do you expect contribute the most to the oxidative potential? And do you have any organic peroxides measurements over there?
Yeah, so I think in terms of, okay, let's go back, I guess I don't have anything for that. Yeah, I'd love to be able to say exactly what organic species are contributing to the oxidative potential of this from these wildfire samples. I think typically, yeah, I think some organic peroxides, as well as looking at like quinones and such, we would expect those to be, those have been shown to have considerable oxidative potential. And so if those are in really high abundance, like we might expect for these wildfire samples, that could be driving the oxidative potential. Unfortunately, with the wildfire samples that we have here, we don't actually have any sort of data to back that up. But with the BB can, let's go back here. Yeah, so you'll see that we have a whole bunch of gas and particle measurements that are being taken. And burning the same sorts of fuels, the boreal forest fuels. And so that we're hoping will maybe better inform what sort of organics we're expecting to see that are contributing to the oxidative potential. Now, these are really fresh emissions, which is why we want to go back, do some burning and do some aged ones to see if there's really a difference in maybe what sort of organics could be contributing, or not necessarily organics, but we expect organics to be contributing to the oxidative potential after it's been aged as well. If that's the same or if it's different, or yeah.
Okay, and one more question that I have was, like, during the different stages of burning, first it was like a flaming and smoldering. So what was the difference you found between the built fuels and the natural fuels? Like, were the natural fuels higher in terms of PM mass concentration in smoldering stage or in the flaming stage?
So in terms of the, yeah, it's hard to say. I think that in terms of the, I think it's a emission factor that would be important there, because we were burning different masses of fuels. So just PM concentration alone. I think very soon there's going to be something coming out. It's not me who's working on the emission factors yet, but there should be something coming out hopefully soonish about the different emission factors in terms of PM mass coming from each of these. I know that some of the differences that we might have observed in terms of just if we go to if we're just looking at PM mass, some issues is like, so the smoldering ones, let's go back to that, right, where really low flaming mass fraction, that doesn't necessarily mean that smoldering contributes has a higher emission factor or anything. The peat was really dense, and we were able to get that to burn for hours, right? Versus when we were burning like dry grass, it was undergoing flaming. We might not have collected as much mass because it burned really quickly and there just wasn't as much mass. We couldn't sustain it for as long. So yeah, I don't have an answer exactly on terms of what emission factors looked like for these different fuels, but hopefully, yeah, that'll be coming out soon.
Okay, thank you, Brett, for an interesting talk. Yeah, I don't see any more questions coming up in the chat box, but yeah, you can feel free to contact Brad if you have any questions regarding burning. So I would request Simon to take ending remark kind of. Thank you.
Thank you, Sachin and Brad and Maria, for a great seminar. Very interesting talks. As I mentioned, we have another seminar coming up in 2 weeks. If anybody wants to give a talk, practice a talk before a conference, let me know and we can schedule that. Also, Sachin mentioned that the in-person conference will take place in Crete next year. The abstract submission is already open. So if you want to join us in Crete, submit an abstract, and that's it for today. Thank you, everyone.
Thank you so
everyone
much.
for joining. Bye-bye.
Thank you.
Thank you.